All right, everyone, it is 5 past the hour and we are live, so let's get started. Before I introduce our next speaker, I'd like to go through a quick reminder for us to check out the sponsor booth, which you can navigate to by the booth icon to your left. Once you're there, you can click into any booth to learn more and to enter for a chance to win some cool swag, such as a custom pair of Nikes. Now, without further delay, it is my pleasure to introduce our next speaker, Stephan Zheng. Stephan leads the AI Economist team at Salesforce Research, which works on deep reinforcement learning and AI simulations to design economic policy. His work has been widely covered in the media, including the Financial Times, Axios, Forbes, MIT Tech Review, and many others. He holds a PhD in physics from Caltech and interned with Google Research and Google Brain. Before machine learning, he studied mathematics and theoretical physics at the University of Cambridge, Harvard University, and Utrecht University. He received the Dutch Lorentz Graduation Prize for his thesis on exotic dualities in topological string theory and was twice awarded the Dutch Natural Hygiene Scholarship. Stephan will be giving us a talk on the AI Economist, economic policy designed using deep reinforcement learning and AI simulation. Please give a warm welcome in chat.
Okay, hi Peter. Thanks so much for having me. Thanks to all the organizers of this event for having me. Today I'm very happy to give you a presentation about the AI Economist. And the motivation for this line of research is that there are many global economic challenges that we face. One example is the increase of income and wealth inequality in the world, which leads to unequal economic opportunities. And this is a trend that has persisted in the past few years. So in the graph, you can see that in the US, the incomes between the top and the bottom of the income distribution have diverged significantly. And this is actually also a global phenomenon. A second example is the rise of sustainability issues. As we all know, in the past decades, global temperatures have risen, and this has massive short-term and long-term social economic impact in the world. And in particular, this is related to all kinds of questions around how our economy and the global climate interact. And to think about how we can address these global challenges, we have to think about economics. So the American Economic Association describes economics as the study of scarcity, the study of how people use resources and respond to incentives, the study of decision-making of those actors in the economy. It often involves topics like wealth and finance, but it's not all about money. And as one funny example, you can think about the Big Mac index on the right, which basically looks at the purchasing power, like how many hamburgers can you buy with your dollar in different parts of the world. And analyzing these kinds of phenomenon is actually a very complicated business. For instance, a key question, if we think about inequality and the climate, is how does a change in economic policy affect the economy, right? And if you open an economics textbook, you might find a diagram like on the right, where the economy is modeled as a huge network in which the government, the households, the companies, all kinds of other actors are interacting with each other. So money is going through the system, but it's not just about money. It's also about how much people work, how much companies produce, what they produce, and so on. And if we want to analyze a change in policy in such a system, this is really complicated because you have to understand how all these moving parts in the economy are going to respond. And this brings us to not just the great successes of economic research, of which there are many, but for today's purposes, I want to focus on some of the limitations and the challenges that economic methodology faces. First, a lot of the models that economists use of people and organizations in this complicated network are too simplistic. That means that people have very simple models of the incentives that drive people and how companies actually function. And even though these complicated models are simplified, it is still very hard to find optimal policies and the responses of these actors in this network if you use the current analytical and computational methods that they use. By they, I mean the economists. Third, there's a severe lack of microeconomic data. So if you open up the newspapers, you often find numbers on the GDP, how much production was there in the entire country. But really at the very low level of the individual people, the companies, it's often very hard to understand the behavior and how people have responded to changes in economic policy. And that brings me to the fourth point, is that actually changing economic policy is obviously very hard because very often it involves the democratic process and deliberation about the effects of a change in policy. And for the reason, it's actually really hard to change policy, but also in effect, it's really hard to see what the actual cause and effect relationships are of policies in the real world. Because once you decide to change one thing, many other things might have changed at the same time as well. Now, the real one of the real bottlenecks there as well is the so-called Lucas critique. So this is a classic argument used in economics, which really points at another issue, which is that historical macroeconomic data doesn't really capture how people would have responded to a change in policy, right? So we think about taxes, which is a subject that we focus on in our work. If we change the taxes in one way and the world also co-evolves with that, it's really hard to do a what-if analysis where we say, let's keep everything else the same, let's only change the taxes in a way that is different from what happened in history, and let's see what happens. Another example is if you think about Fort Knox, which is a big fortress that has gold in the US, you can ask how much should Fort Knox spend on protection, right? But the Fort Knox has never been robbed. So it's really hard to understand if it would have been robbed if it had less protection, right? And so all these examples point to the really hard, the issue at the core of economics, which is that we are observers in some sense of the economy, and we can only actively intervene so much in the real world. And so what this points to is that as a discipline, economics really lacks the economic simulations that are based on so-called micro-foundations, where micro-foundations refer to the fact that they lack these individual models of people and firms that would allow you to do better counterfactual what-if analysis and in the effect design better economic policy. So the AI Economist, taken generally, is a program to infuse economics with AI that will help us get around some of these barriers in economics research. And this consists of, roughly speaking, 3 pillars. The first pillar is big economic simulation, in which we try to build models of the economy that are based on human-like agents, firms, and other individual actors. And so really, we're trying to build the economy or model of the economy from the ground up. Second aspect there that's really important is that you have to think about the natural behaviors of these agents and firms. And this requires, in a concept like bounded rationality, that describe how people are actually not completely like a cold rational agent, but are driven by all kinds of cognitive biases and other things. And this means that we have to think carefully about how we model the incentives and the interactions of all these agents at the ground level of the economy. Second, from a machine learning point of view, there's the need to do multi-agent learning, and in particular, deep reinforcement learning. And a big question there is this: how can you use those methods to give explainable policy advice, right? So in the end of the day, if we have some recommendation of how to change economic policy, we better explain why, right? And this is still a big issue when we talk about deep reinforcement learning and other popular techniques of the day. And thirdly, there's a need for hardware acceleration because many of these machine learning methods are very data hungry. They take a lot of time to run stochastic gradient descent, for instance. And when we talk about big economic simulations, we really need hardware acceleration and efficient software that allows you to do that kind of research. And lastly, it's important to think about real-world applications where we can get the micro-level data, where we can look at the robustness when we take something from the simulation to the real world, and think about the trade-off between simplicity of the policy and how effective it actually is in the real world. Now, this is a huge program, and in the rest of this talk, I want to highlight some of the projects that we've done in this research program and where the future might take us. The AI Economist, as we showed in the first public work, looked at improving quality and productivity with AI-designed income taxes. So this is now open source, so you can go to this GitHub link to look at the research yourself in depth and play with the code. And at a high level, what this project was studying was a very simple economic simulation that you can see on the right, in which you had 4 agents that were collecting resources and building houses. Now, there are 2 levels of reinforcement learning in this project. At the bottom level, the workers are collecting all this wood and stone and so on, and they're working and making money. But at the same time, there's also a government, or in economic nomenclature, social planner. And the social planner uses taxes to maximize social welfare, and that is equality and productivity. The important distinction of this work is that all the behaviors here are learned by reinforcement learning, and they're not pre-programmed, as is very common in economics research. And what's important here is that the system looks very simple, but in fact, there are no explicit solutions for how the optimal agent might behave in the system. The economic theory is simply too limited to do so. So we set out to solve this problem of finding the optimal tax policies and the optimal responses by the consumers using reinforcement learning. And that takes us to 2-level reinforcement learning, because both the workers and the government are learning in the system, and they're really co-adapting. So as soon as the government is changing its tax policy, the workers in this simulation are going to respond to that in the way that's that yields maximal utility for them. And the important learning challenge here is that if you look at the decision of a worker in a system, right, during training, the decisions that the worker might have thought that was optimal in the past might not actually be optimal in the present, right? And this gives you a huge stability that's akin to training again. But in this case, it's in the sequential case, so it becomes even more challenging. And the way that you see that in our experiments is that you can measure the social welfare objectives. So that's the product of equality times productivity. And in our work, you see that the green curve here doesn't go up monotonously. It actually goes up and down. And this up and down behavior is really because of this co-adaptation problem, right? So as soon as the social planner finds a way to maximize social welfare, the workers might respond in turn, and that actually lowers the social welfare again. But at the end, our 2-level reinforcement learning method still ends up on top compared to some other baselines. At the end of the day, that allows you to compare these different worlds in the simulation. So on the left here, you see the free market, where there are no taxes at all. And on the right, you can see the AI Economist. And what is very salient about this is that the AI Economist achieves a more equal distribution. So if you look at a dark blue agent, it achieves about half of the income in its world, as opposed to 2/3 in the free market. Now, if you look at the product of equality times productivity, society is actually better off on the whole, because this social welfare metric is in fact higher than in the free market. And that's not just true in that one example I showed you. This actually is true if you repeat this experiment many times. So if you look on the right, the equality times productivity metric is statistically significantly higher by at least 16% over the baselines. So those baselines include the free market, the US federal progressive taxes, and also something called the Saez tax formula, which is the classic optimal tax result from economic theory. So I encourage you, if you want to learn more about this, to check out the paper that's on the archive. Now, since that income tax work, we've also been extending the scope of this methodology to other applications to research how it might work in the real world. And I'll give some vignettes. And the first one is some work we did around COVID-19. So we took a COVID-19 simulation of the United States, where we simulated the number of cases and deaths due to COVID-19, but also modeled unemployment and productivity. And this was based on real data that is publicly available in a Johns Hopkins University data set. And the goal here was, again, to analyze how policies at different levels impact the course of the COVID pandemic. And in particular, we simulated the policies for the states and the federal government in the US. At the level of the states are determining how stringently they are responding to the pandemic. So that means, for instance, closing down restaurants, closing down businesses, limiting travel. And at the federal level, we looked at how much federal subsidies the government might give in order to promote stronger lockdowns. And what the system found is that at a high level, that harder and faster responses can halve death. So if you look at the death rate on the right, in the bottom right here, you can see that the blue curve is what you find in this simulation. And this turns out to be significantly lower than what happened in the real world. The second vignette is a project that we ran on real business cycle models. So if you're familiar with economics, a business cycle really means the periodic ups and downs in the market. And in particular, RBC models are adding companies to the simulation. So if you think back about the income tax work, there were workers in the government. Now here we're adding companies. And again, we're asking in this complicated network, what happens when all these agents are being strategic and can use reinforcement learning to learn how they should optimally behave. So what we found is that from a game theoretic point of view, finding these equilibria is actually quite hard. But if you extend the methodology that we've used for the income tax work to this setting, where now we have 3 types of agents instead of just 2, you can actually find the Nash equilibria of the system. And by Nash equilibria, it means that if you look at a single type of agent at convergence, does that agent want to change its behavior? And it turns out that empirically, the agents want to change their behavior a little bit, but the deviation only causes at most a 5% change in their reward. So it is something that's called an approximate Nash equilibrium for the system. And this is quite hard because in economics, people often talk about knowing that there are multiple equilibria, but actually finding them is something that is just very hard. And we show that using reinforcement learning, you can actually learn this equilibria. And secondly, another thing that we found is that if you look at the taxation policies, you find something that's similar to the previous work I showed. That is that the AI taxes, again, outperform tax baselines in this more complicated economic model. Third, we also had a project where we looked at more human-like agents. And so we asked, like, how do teams of human-like agents behave? So if you have a manager and the manager's employees, and let's imagine that all these agents are now reinforcement learning agents, can we capture some aspect of what human-like behavior looks like? And a significant component of that is because of something called rational inattention. So the basic idea here is that time and energy are scarce resources. And as people, we are going to choose what to pay attention to, because we don't have all day to read all the details in a very complicated textbook, for instance, right? And so by modeling inattention, we can model many forms of bounded rationality. So in this project, we found that if you look at this manager-employee relationship, that you find something that's not quite intuitive, or at least it's something that economists have not really studied in these complex sequential manager-employee simulations. And we specifically found that if you think of a manager that doesn't have enough time to pay attention to all their employees, you find that the rational policy for the manager is actually to take a better safe than sorry approach and raise wages in lieu of knowing how much each individual employee actually contributed to a project. So the idea is that the manager doesn't really know who to reward more and who to reward less, because every person might contribute a different amount of work to the project. It's better to raise wages across the board, and this actually is better. It's a better outcome for the planner than spending time on figuring out who's actually performing better or worse. So this is a very interesting effect. It's a bit counterintuitive perhaps. And again, this is something that economic theory doesn't really have the ability to analyze in full detail. But using reinforcement learning, we actually find some very interesting phenomena, and we show that actually this methodology is more powerful and lets you analyze these models of human-like behavior. Now, lastly, I want to highlight a project that goes more to the systems side of this. So as I mentioned, a big part of this AI simulation-driven economics research is scale, right? One aspect, one bottleneck in previous simulation-based work really was that a lot of times the simulations were either very simple in terms of the models for the agents or in the scale of the simulation, like how many agents can you actually fit in that. So in order to contribute to faster simulations, we developed something called WarpDrive, which is a GPU-accelerated multi-agent reinforcement learning framework. And again, if you're interested in this, you can go to GitHub and look at all the details and play around with it yourself. In a nutshell, what WarpDrive does for you is that it lets you run multi-agent reinforcement learning with thousands of agents and copies of simulations in parallel using GPUs. Compared to like other GPU, CPU implementations of reinforcement learning, there's actually no back and forth copying of data in each cycle of the reinforcement learning loop. Furthermore, it's implemented in Python. It does require simulations that are written in CUDA right now, but we're working on making that easier as well. And it works with PyTorch and uses PyCUDA under the hood, right? So the idea is that you can take your favorite PyTorch Python implementation of reinforcement learning with your neural networks, hook it up to your CUDA simulation, and use WarpDrive to run the entire loop. And what we found is that this particular way of doing multi-agent reinforcement learning gives you on the order of 100x higher throughput, right? And you can really train at million steps per second. Now, I don't have enough time to explain in full detail how this architecture works. Again, I would refer you to the GitHub page for that. And we also have a paper on arXiv actually about this. So I'll just show you a nice animation of a toy tag environment that we implemented. So in this tag environment, we have hundreds of agents in blue and 4 hunters in purple. And we found that using WarpDrive, the scaling behavior is very consistent. That means that in purple, you can see how many samples per second we get with the GPU implementation in WarpDrive. And in blue, you see how many samples per second a CPU implementation gets as we increase the number of agents. And you can see that this is a log-log plot. And even in a log-log plot, the gap here grows exponentially, which is, shows you that like WarpDrive scales much better than many, many agents. Now, we also have a GPU implementation of the COVID environment I mentioned before. And in this case, we find that if you look at this more complicated simulation, then simulation plus reinforcement learning training together is still 24 times faster. This is in the first iteration that is maybe not quite hyper optimized, but again, 24 times faster means that instead of waiting for a day, you can finish your experiment in a matter of hours. Again, if you're interested in this framework, please check out the GitHub link. So I'll close out this presentation with just one slide about the future and where all of this is going. So I only have 20 minutes here to tell you about all these projects, and in all these projects you've seen that we can build these AI simulations that are starting to capture more and more facets of the real world. And even though, of course, these are still models, the promise of using AI in all these simulations means that there's a lot of potential for future research. So firstly, there's a huge need for new tools for economic and policy making. We think that AI is a key component there, but it also means that we have to do a lot more work around, for instance, responsible data collection and using that to build more fine-grained economic simulations. We have to onboard economists with artificial intelligence and computer science practices. Very often, you'll find that economists are not really familiar with these new tools. They code in, they do statistical analysis in R, for instance, but they don't really use Python or Matplotlib and the whole data science stack that this audience might be more familiar with. And also, we need to work together to test some of these policies in the real world, right? That is going to be a big project, and it really will only happen if we work together. Secondly, AI researchers still have a lot more work cut out for them. We have to develop more methodology that involves building even bigger, more realistic simulations. We have to think very carefully about what the convergence in these types of multi-agent reinforcement learning experiments looks like and what it actually means. Do we find all the equilibrium? What happens if the world is not actually equilibrium? And that's in fact like that's what happens in real life. And so there's still big questions like how does equilibrium analysis actually inform the non-equilibrium behavior and analyzing that non-equilibrium behavior in the real world. And thirdly, there's still a huge gap around explainability, simplicity, and robustness. As you all know, neural networks are great because they have a lot of flexibility. They can discover really complicated patterns in data. But when you actually try to explain how this neural network arrives at this decision, then it becomes much harder. And it's very likely that people will not accept a black box neural network as as an economic policy recommendation if we can't actually explain all the pros and cons and the why of that neural network policy. So all of that is still also an active area of research, but this potential of AI is huge, and so hopefully that will motivate you all to look into this and work on the future. So if you are interested in working on this, we're hiring interns and full-time employees at Salesforce. So if you're interested in that, you can look at the careers page on Einstein.ai. And we have a lot more resources for you to look at. We have papers and blogs and so on, which you can find on our website. A lot of the code for the simulations and reinforcement learning is now open source. So I encourage you to go look at the AI Economist repo and the WarpDrive repo. We also have workshops that we organized. One was held last year. This is a typo, actually. This was NERPS 2020. Yeah, and we are also on Slack. So if you have any questions, you can find us there. And we're happy to discuss all of this research and any questions you might have. So thanks again for having me today. And I'm happy to take any questions if you have time.
Awesome. Thank you so much for the insightful talk, Stephan. It's very interesting to see the AI economist use case and it being in action. And I really think it's amazing that you have everything open source and available. One of the questions in the chat is just, is it possible to kind of, I guess they could just copy from the slide right here to kind of access your GitHub. I have a quick question about, I guess what you mentioned about explainability, right? Economists and policymakers, they really don't want a black box, but to what level of explainability do you feel would be, I guess, a area where they would be comfortable with? Is it being able to see each of the agents and how they behave and what really influenced their behavior, or is it more of a macro scale?
Yeah, that's a complex question. To some extent, it's a back and forth, I would say. I think one of the things is definitely what if scenarios. So people would ask, what if the income distribution is not what you have in your simulation? What if we have 20% more low income families in the simulation? What would happen in that case? It requires, to some extent, a statistical analysis of the data and seeing how well your policies and your simulations fit, of course. So those are some of the practical points. But in reality, you can look at current economics research where people really like linear models, right? So that's almost a golden standard in economics research. And in linear models, people have very well understood statistical analyses that you can run, statistical tests that you can run, and that's typically accepted, right? So understand to understand your analysis. So with these neural networks, it's obviously very different from linear models. So I would say that somehow we need to bridge those two paradigms, right? And I think people do a lot of work on that. And as far as policymakers go, they often rely on economists to do that statistical analysis. So it also relies on us to convince the economists that we have a similar rigorous statistical pro and con analysis of the models and the policy recommendations. And yeah, so that's a partial answer. It's a big topic.
And I guess to kind of also show like proof of concept, have you guys done a lot of work into kind of modeling previous economic policies during that has a lot of data related to it, and see how well the simulation actually predicted versus the or kind of worked versus what really happened in the real world?
Yeah, the COVID project got at that to some extent, right? So we did do extensive cross-validation of the simulation and of the simulation parameters. So what we did there was we said we take the data, we find some inferred infection rate and a recovery rate, and we can replay the real world policy in that simulation and see if the outcomes are still the same. So that was true. That's one example, but there's nothing public yet, at least not public yet, but we are thinking about ways of doing what you said. So taking a longer time frame, looking at more macro scale phenomenon. So work in progress, I guess.
I see. I'm guessing WarpDrive kind of accelerates that because you're able to simulate a lot more. I guess that kind of answers our question in chat of how well do your human agents react to changes in tax policy and whether it matches what happens in real life, right? Because the COVID simulation kind of looked at that, right?
Yeah, the COVID simulation was a macro level analysis because you're looking at a whole population. For the income tax project, it's a more micro level study. So in that case, what you see is that the AI agents want to specialize. So we said, okay, specialization is one feature of the economy that they managed to reproduce. On the archive, you'll find that there's a section where we did do a small human user study. So we actually asked real people to go play in the simulation. And then we found actually that there's an AI tax policy that was learned that is different from either progressive or regressive taxes. And when you apply that tax policy to the real people in the simulation, then it still improves social welfare. It still improves equality and productivity. So we do have some early indications at a small scale that the policy transfers well to real people in the simulation. And so if within the constraints of the simulation, people behave very differently. That's one thing. And then the AI policy still works well, it seems. But I'll say as well that at the low level, the study was still quite small. So you see a lot of noise and variation in the outcome. So it's something that we're thinking about ways to expand that, but it's not public yet. Yeah.
Well, that's really exciting results in the big, just preliminary results, right? I guess our next question is more so about kind of Salesforce's interest in economic research. Are they funding other research not directly related to their CRM offering, and how that direction?
Yeah, we have a small part of the research organization that's dedicated to AI for society. So it's more about social impact of technology. It's something that the company as a whole cares a lot about. one of the distinguishing factors for Salesforce is that it thinks about technology as a driver for social impact, positive social impact, I should say. And so, yeah, part of the research team gets to do research that is not directly product focused, but it does fit the overall objectives that the company hopes to achieve with technology. So yeah, we do also have research on protein design, for instance. So there's some biomedical research. Yeah, so there's like a part of the organization that's focused on these kinds of things.
And I think that should be it for, actually we have one more question. Do the models capture diverse groups in any way? For example, an objective function that maximizes social or economic welfare, taking into account small but already marginalized groups?
Yeah, so the diversity or the way that the agents in the income tax simulation are different is in terms of their skill and their starting positions. We have some unpublished results, hopefully soon public, but where we also look at other scenarios where some agents are more at a disadvantage than other agents. So, that is not all levels of diversity as we see in the real world, but broadly speaking, we see that the AI system still finds a way to improve equality for everyone, right? So because every particular setting has its own sort of a particular way or a particular aspect of inequality, so to say, right? Because some agents might be in a corner where there's very few resources. So broadly speaking, we find that the AI system still works well in terms of this equality, productivity objective. Yeah, and then in the future, I would say that like part of making these bigger simulations is that you want to make more representative simulations, right? So if you have more agents, then you also have the opportunity to have a more rich distribution of people, different income levels, different skill levels, different geographies. And that's partially, really tied to scale, right? So that's why we built this WarpDrive framework, because our income tax implementation is great, but it starts to get slow, right? Once you go beyond like 10 agents. And so, yeah, now I think with WarpDrive, you can really run these things with 1,000 agents. And then you can really start to dig deeper into like all these aspects of representation and how you can make sure that the system still pays enough attention to the people who are less privileged. Yeah, so I think that's a very exciting direction for future research. It's totally open.
Yeah, definitely. It sounds like there are a lot of really exciting unpublished work that it's going to hopefully come out soon, and I'm sure everyone here is super excited to read it. Yeah, I think the future of the AI Economist seems really exciting, and I really hope to see some of your future works. Thank you so much, Stephan, for joining us today, and thank you everyone for joining this talk.
Yeah, thanks so much for having me. Thanks for organizing this event. It was really great.
Have a great day. Thank you.
All right. Take care, everyone.